Hi everyone, welcome back. Today's lecture is about processes. This is one of our longer lectures, so feel free to take this in a couple of different sessions if you like. So to get started here, the definition of a process that we're using is an instance of an executing program. And that instance has its own collection of resources that is required and that it uses in order to run effectively and efficiently. Process management is a key component of our multi-programmed operating systems. So the operating systems have to know how to start and shut down processes, which they can do. And from our perspective, we need to know how to start them up and shut them down by asking the operating system to do these things via system calls. So some of the things that a process has, first of all, is a unique identity. We call that the process ID. The process ID is stored in terms of a variable in C in a type called a PID_T. And that just helps so that we have consistency when we're passing around these process IDs, but it's easily converted in and cast into an integer. And the function is just get PID. Very simple. Each of these processes has a virtual address space, so they believe that they are starting at byte 0 in memory, but of course that has just been virtualized. They have a chunk of memory reserved for them, but from the process's perspective it starts at 0, whereas actual RAM it might start at some, who knows what random location it starts at. The process knows about the program data that it has, the variables that it's tracking. It knows who started up the process and the groups associated with the files that are being used. It knows about the UMask value, so when it is asked to create a file, what the default permissions are. The process has an execution environment that is unique to itself, and that would be things like environment variables and what current working directory it's using, any open files that are active. Talk more about that at the end of the lecture. It knows about its resource limits, its own scheduling priorities, so how much attention, how much time on the CPU it will get, and a bunch more. There's a bunch of other really esoteric things that you can find on the Exec man page. So comparing these programs to processes again, a program is the executable code, for example, like a recipe in a book. And a process is a running instance of that program, so you can envision a cook making the recipe. And we can have more than one process be concurrently executing the same program code, and each of them have separate process resources. So you can see that we've got multiple cooks that are here working on setting up this meal, and each one has their own plates, their own utensils. They're using memory. In some cases they might be accessing the same memory, in other cases they have their own sections, but it's multiple instances of it all running at the same time. And we might also have, we definitely have all these different processes are running different sets of code. So one process does not have to be the same as another, and certainly for the most part they're not. So let's look at some of the important process states that they can be in. So the one that we might think of most readily would be the state that's called running. It's just that that process is currently on the CPU, processing through its executions step by step. Another one would be waiting. This would be when it's waiting for input and output. So if it's blocked, for example, on some read call to a hard drive or a write call to a flash drive, maybe it's blocked on that. There might be a timer alarm that is causing it to just wait, or there could be some signal. Anyway, these are all known as blocked states. So any one of those causes the process to go into what's called waiting. Another one is runnable. And runnable is when the process is not waiting for anything and could be put on the CPU at any time, it just hasn't been yet. And there is a fourth error state, or not really an error, but it's definitely a non-desirable state, something that we want to get the process out of as soon as possible, and that's the zombie state. And this is for once the process has terminated and it's merely waiting for the parent to notice that it has terminated so it can be cleaned up. So how do we create a process? Well, we don't. We can have the shell do it for us though, and we do that by using a system call. System calls are what ask the operating system to actually create the process for us. And in our case, we use the shell. The shell then interacts with the operating system, which does it for us. So we have our major shell writing assignment as part of this course where we do this a lot. So Unix is going to provide a C API for creating and managing all of these things explicitly. So we will show a bunch of those various functions in the material. Here are the primary ones. So the top one is called fork. And fork is going to be used to actually spawn off copies of our processes. The exec family is used to execute new processes. Exit is used to terminate. Wait and waitpid are used to clean up resources from child processes. GetPid gets the process ID of whatever process runs it. And getEnv and putEnv are for getting and setting environment variables. So how do we actually start a new process? To do this, we use a function call called fork. And what fork is going to do is it's going to start in process A. You call the function fork in process A, and it clones your process into a new one. And they're nearly identical. They're both running exactly the same code, and they're both continuing on from where that fork call occurred. They are not exactly unique, or they're not exactly the same though, because they both have different process IDs, and each one of them is going to return a different value from that fork call, and we'll show an example here in a second. Process B is going to get copies of all of the open file descriptors for process A. So whatever your original process started with in terms of files that are being opened, log files, error files, things like that, process B will also have open file handles on those and can read and write values from the same files. Process B also has all the same variables because it's the same code that's running. And all of those variables are set to the same value as they are in the original process that spawned the new one. But the copies of the copies of the variables that are in the new process, they're all separately managed. So process B can change the values of those variables and not worry about it, or not worry about messing up what's in process A. And more here. So let's take a look at our actual primary example for using fork. And I recommend that you stay on this slide until you fully understand what's going on here. So let's take a look at the top. First, let's cat out our program. This is forktest.c. It has the standard bunch of header files that have to be included. Some of the types and unistandard, those are used in terms of referencing our PID and our process IDs. So we start up our main function here, and we're going to declare basically what's an integer, but it is stored as a PID underscore t. This is where our process ID is going to be stored. We're going to initialize it to -5, which is kind of a way of saying this is a value that we have explicitly set to be a bogus value, because this thing can return other values that are commonly used for initialization, like -1 or 0, and having those values appear in this variable might confuse us as to whether or not the function returned or whether it was still uninitialized, or from our initial initialization, that's right. So in this case, we're setting it to -5 to be more clear about what's happening. And then we set some number so we can mess with it here in a minute. Now here is the fork call. We call fork, and we assign the return value of fork to this spawnPID variable that we had. And that is now going to have a new value. So let's go ahead and switch on it, and we can then track the different cases for what can happen. So first of all, if this thing ends up being -1, and something horrible happened, the fork call failed for some reason, and probably the most likely one is that the user who is logged in has no more authority, no more permissions to spawn another process, because there are limits in terms of the number of processes that you can create at once when you're logged into a shared server. So maybe you've exceeded that limit, and so you can't create any more. So that might be a case. Case 0 means that the child is the process that's currently running. So I can take, for example, that variable 10 and add 1 to it, and then I can print out I am the child, and I can print out the results of that 10 change and then exit out. Break exits out of the switch statement, and then I get this print that says this will be executed by both of us. However, any other value, so other than -1 or 0, any other value means that we're in the parent. And for the parent, we're going to modify 10 in a negative direction, print out that we are the parent, and then break and once that break happens, it gets us out of the switch, and then we'll get the same thing. This will be executed by both of us. So again, through the three cases, if something went wrong, fork is going to return a -1. In the child process that is running this same copy of code, which begins life here at this fork call, it will immediately go to this branch. And case 0 is when spawn pid has been set to 0 by fork. We know we're in the child process. The parent process, on the other hand, which just executed this fork command, continues along its merry way. And it hits this switch statement and goes to the default because spawn pid is neither -1 nor 0. It's anything else. And in particular, the spawn pid is the process ID for the child that was just created. So the parent knows the process ID of what it just created so that it can, for example, delete it later, check on it later, whatever it needs to. So again, I recommend that you hang out on this slide. Go ahead and rewind if you need to, if you want to. So make sure that you understand that there are now 2 instances of code running at this point, and that at fork here spawns the new process. The parent continues on. The child wakes up to exactly the same code file starting at this line and continues on its way. Here are the results. So when we run fork test, the child says, I'm the child, and 10 has been changed to 11, and it says this is executed by both of us. The parent says, I am the parent, and it's changed its variable itself. And they both report that the line that says this is going to be executed by both of us. So the order of this is up to the operating system and the scheduler. You don't know which one's going to go first. Is the child going to go first? Is the parent going to go first? Are they going to be interleaved because of when they're reporting when the printf statements are firing off? That's up to the operating system and its scheduler. About the only thing we can say is that the I am this child line is going to occur before the child's version of this will be executed by both of us, and the I am the parent line will be executed before the parent's version of this will be executed by both of us. That's about all you can say about the results of when these things happen. So some of the key things that will be inherited by the child, let's look at those. So first of all, obviously the program code, because it's the same program just running in a different instance. It'll have all the same credentials, so the user IDs of what spawned it for the user and for the group, so the user IDs and the group IDs. It'll have the same virtual memory contents, that is, the variables will all be the same, so the stack and the heap are all the same, the data segment variables are all the same. They can be changed, of course, from then on, but they start out being the same. All the files that were open stay open for the child, and the child gets its own file descriptors for those files. It can close them independently from the parents. There's a special flag called close in exec, which we'll talk about in an upcoming lecture, but that particular flag is inherited down. Any signal handling settings are inherited. This is key for when we're trying to manage whether or not the child can receive a signal or not. So the parent's configuration. So think about the trap line that we talked about in block 1, the trap command for a bash shell script. That trap command is registering a shell script for a particular signal type that might come in. In this case, we can do the same thing in C. We can register our program so that when it is spawned as a process, it can pay attention to certain signal types. Well, those signal handling settings are passed into the child as well. So the child also knows about its process group ID, which is a little bit different than the credentials that were used to spawn it, right? It has its own group ID, and it also knows about the user and group that spawned it originally. It knows its current working directory, and it knows the controlling terminal that started it up, and a few other things that are not quite as important for our purposes. Some things that are unique to that child, though. So it has a unique process ID, and that makes sense. That process IDs are guaranteed to always be unique for the set of running processes on the system. The parent process ID is going to be different, and that should make sense because the parent that spawned us is, the parent. It's the parent that spawned us. So the parent process ID changes to be what just happened. So when process A spawns process B's parent is now process A. Process A's parent hasn't changed. It's still whatever spawned it originally. What's unique to the child is its own copy of those file descriptors. So they start open, but the child can modify them. All of the process text and data and other memory locks are not inherited. So if there's any locks that were set up for the previous process, those are undone. And any pending signals that are going to be initialized to the empty set. So if there was a signal that was just about to hit the parent process and it hadn't yet been processed, and you forked to a new child, that child will not receive the signals that the parent is going to be hit by. Alright, so fork kind of forms a family tree. Each process spawns the next in kind of generations of processes that come. So if I have process 4932, that process might just keep running here. But I can fork off a new version, which is process 6923. And then that process maybe forks another one, 7877. But each one of these are copies of the original 4932 process. They might be running different sections of that program, so maybe they're in different functions, but each of those processes contains the entire code of the original 4932 process. Here's another one that it spawned after spawning other ones. That's just fine. When they terminate, let's talk about ways the child processes can terminate. So a child process can exit for two primary reasons here. First of all, it can complete its execution and exit normally. So we had our parent process, it spawned off a child, and the child finished. It ran to the end of its functions, the end of its process, and exited like normal. No problem. Nothing strange there. Maybe we get a successful exit status, so 0. The other case might be that the child process encountered some error condition or some other event that caused it to want to terminate early, so it goes ahead and exits itself, kills itself off, and it returns some non-zero exit status. There's no problem with that too. Either one of these, though, it's the child process that is doing the exiting for whatever reason. Another case is going to be that the process was killed by a signal. So maybe it was sent by a signal that by default would terminate a process, and the child wasn't paying attention, didn't catch the signal, and ends up being killed by that signal. So the process gets killed by the signal. That's different than the child receiving a signal, catching it, handling it, and then deciding to terminate. Those are two different things. That would be, one of these things in one of these upper cases here. We're talking about a case where the child was sent a signal that by default would kill a process. The child didn't pay attention and ended up being killed by it. So how do the parent processes check to see if the child processes have actually terminated? So two primary ways. Both of these commands are going to check for termination of child processes. For both of them, we're going to pass in a pointer to which the operating system is going to write an integer. And that integer is going to identify how the child exited. And it's not a simple integer. It's not like it's just a number that we can read at any time. That particular integer is kind of built up through a bunch of different bits that are set. So you can't just look at the value of it and think that it's some human readable value, because it's not. You have to examine it with a few different macros to actually learn what happened. So let's talk about our various functions here. So we have our wait function, and wait is going to block until any one child process of this parent process has terminated. And if that's happened, then it will return the process ID of the terminated child when you call wait. But remember, it's going to block until that happens. So if your parent process calls wait, it then stops processing. It won't do anything else until any one of its child processes terminates. And at that moment, that will cause the parent process to wake back up, and the value of wait that's returned will be the process ID of the terminated child. Now, if a child has already terminated when you call wait, then wait will return immediately with that process ID of that terminated child. So wait PID, on the other hand, will block also when you call it, until the child process with the specified process ID terminates, or perhaps has already terminated. And that will return the process ID of whichever one had just terminated. There is a way to pass in a flag to wait PID that says don't actually block. So if that process has not yet terminated, go ahead and resume executing, and then you just have to check the values of what WaitPid is doing in order to figure out whether it terminated or not. But there is a flag called, I think it's something no hang, and we'll look at that. But the no hang flag says keep running, but don't actually block if the process hasn't terminated yet. Let's look at some examples. Here's the two function signatures for wait and waitpid. Both return the process ID of the terminated child, or some error value if something wrong happened, or if the process had not terminated yet in the case of waitpid. So with wait here and waitpid, you'll pass in this child exit method int, and again, it's not an int that's human readable. It's what the function is going to write the value back into once it's actually terminated. For the waitpid version, you also are going to pass in the process ID of what you're looking for and then some options. So examples. This one, block the parent until any child process terminates. This is the easiest case for calling wait. You call wait, pass in your variable that's going to be written to eventually whenever wait finishes. Once it does, then we get the child process written into here, and we can go examine child exit method to see what happened. This one blocks this parent until the specified child process terminates. So we can pass in what we're intending to look for, and here is where the method of termination will be written. Here we're saying no options, and then the process ID of what actually terminates is written back into here. But since we told it what process ID to look for, you can actually just use the same variable in both these cases here, but I've split it up here just to be more clear about what's happening. Here we are obviating the need to use the wait function at all, because this one essentially does the same thing, except we've added this no hang flag for explanation. But this is childpid as the return value, but waitpid we're not giving it a process ID, which basically means check if any process has completed, just like our wait version does. Here's where the exit method is going to be written into child exit method. And finally, this flag, w_no_hang, that says don't just block, but check if any process is completed in it. If there have been no completed processes, then continue running. So that's handy. Otherwise, we would just pass a 0 into this thing and to give it no options, and then it's exactly like our original wait up here. Now, this thing will return 0 to this child process ID return value if there have been no terminated processes. That's because of that no hang value here. All right, so this version here, again with no hang, says check if the process specified is completed and return immediately with 0 if it hasn't. So as opposed to checking for any, here we're specifically saying check for a specific process ID. Okay, so placing waitpid, let's do a little example, a little more complete example now of a parent spawning off a child and then waiting properly for that child to terminate. Here's our output, what it's going to look like. Fork wait test, that's the name of our program for once it's compiled. Here's the cat version of it. The parent is going to say, my process ID is 3311 and I'm waiting, and the child says, the value that I received was 0, I'm exiting, and then the parent says, child process terminated, I'm exiting. So we see that order here. Let's take a look at the program here. Here are the variables we're going to use. They are initialized to a junk value that we know about, so a known junk value. Here's the fork call, just like we saw before, the spawnpid result. The -1 value says something horrible has happened, go ahead and exit the whole thing right here. Here is what happens if the child process is the one that reaches this block of code, and that can only happen if spawnpid has been set to 0. So in that case, we're saying that the process ID here is this spawnpid that we received, and that turns out to be 0. Now, obviously, that's not the actual process ID for the child. It's merely a reflection of what spawnpid is. If we want to get the actual process ID for this child, we would instead use something like getPid. We'd consider putting in getPid here to see the difference. For our parent, here, instead of using a switch, I'm simply saying, well, if I didn't have some horrible error result and I'm not the child, then it must be the parent. So let's run the parent code. Here the parent says, I'm waiting, and it's waiting specifically on the spawn PID for the child, which will be filled with the right value. Then we run the wait PID function. And what this does is it's going to block because I didn't pass in the no-hang parameter. And we're going to write the exit method for the child into this thing whenever it finally completes. And here's where I pass in the spawn PID of what I forked off and got the value for originally up here. So this thing stalls and waits for an indeterminate amount of time. When it finally returns, the parent says, I have terminated, and then I've exited. Up here, the order of this parent and child line is again up to the scheduler. So this could have been in either order. This line is always going to be after the first parent line, but the parent and child, these two lines could have been done in any order. The likely reason why the child line was second is because this spawned process ID, it takes time. It takes time for the child to initialize, to create itself, to be spawned off. Meanwhile, the parent has had time to talk about itself. Okay, so let's check that exit status and see if we can learn something about how these processes have exited. So with both of these, with both wait and wait PID, we can identify two different ways that that process could have terminated, and we talked about these originally. If it terminated normally, meaning it ran off the end of its code, it called exit, it called return for whatever reason with whatever value, then we can use this special macro wIfExited. We can use this ifExited macro on our child exit method integer. Remember, you can't just look at child exit method. You have to run the ifExited macro on it. And if this thing is not 0, so if it's non-zero, then we know that the process exited normally. That's if exited. If this is true, then it exited normally. And if that did occur, if we did in fact know that it successfully exited, then and only then can we look at the actual exit status. So this would be like, exit 5 or return 0 or whatever it is. We can actually get that integer out by using the wExit status macro on the same integer, and then that will tell us what the integer actually was. So remember, you cannot get the return value of a process by examining the child exit method integer. You can only get that by running the exit status macro, and you can only run the exit status macro if you're sure that it exited normally, which you would do by comparing this. And again, example coming up here in a bit. It's actually pretty simple once you see it. The other way here is if the process was terminated by a signal. And in that case, instead of having ifExited return non-zero, what we have here is that the wIfSignaled macro is going to return non-zero. So here, if signaled on that same exit method integer, if that returns non-zero, then we know the process was terminated by a signal. We can get then the terminating signal, so what actually killed this process, by using the wTermSig macro on the same child exit method integer. So again, to repeat similarly like the previous slide, you cannot get which signal killed the process by directly examining child exit method. You can only get that terminating signal by examining wTermSig. So as a bit of a spoiler, because we're going to have a whole lecture on signals coming up, each signal, we've seen them as sigint and sigterm and sighangup. Each one of those also has an integer. So internally inside C, inside Unix, you can refer to the signals by their integers as well. So this thing returns whatever integer that is, and there's a mapping between the two. Let's talk about the exclusivity of these two macros. There's a couple of flags that you can use in waitPID, and those are the wContinued and wUntraced flags, and they're pretty non-standard. There isn't really a reason to use them for our assignments here in this course, so let's assume that we haven't. And if you have not used those, then only one of the ifExited and ifSignal macros will be non-zero. Only one of them. The other one will be 0. So if you want to know a child process died, then you do need to be aware that both of these macros are involved. So if one is 0, the other will be non-zero, assuming that both of these were not used, both of these non-standard flags. So if the child process has terminated normally, do not run termSig on it to try to get some terminating signal, because there was no signal number that was involved in the termination. Conversely, if the child process was in fact killed by a signal, do not run the exit status macro on it, as it has no exit status. So exit was never called, return was never called, so you don't have to worry about that. As a little aside here, the return in C can be written either with a little functional parentheses notation, or you can just put the number directly afterwards. Either are valid C. So again, we use, here's the if it exited, we can tell if it exited with the if exited macro, and then we get the exited method, the actual exit status number out with the exit status macro. We can tell if it was signaled by using if signaled, and we get the actual terminating signal out with wterm sig. So both of these are involved, and there's certainly no problem in checking both. Out of a sense of paranoia, because everybody is in fact out to get you, checking both to make sure one is non-zero and the other is zero is certainly prudent. So here's an example of doing this. We have our child exit method integer defined at the top. Here's a wait command that is going to assign its value, or its exit, the child exit method into here once it finally returns, and it'll be writing the process ID for what was terminated into this variable, child PID. Then we're going to examine child PID to see if, once this thing finally returns, if there was some horrible problem, and exit if there was. Then we're going to check what happened. First of all, let's use the if exited macro to see whether this thing terminated normally, and we'll check our child exit method integer. So if this is non-true, and that's how we know that something is true in C, 0 is false, anything else is true, from a Boolean evaluated as integer perspective in C. So if exited returns non-zero, then we know that it exited, and we can output that. The process exited normally, and now, and only in this case, can we call exit status on this thing and get a value that makes sense. Exit status is actually the exit status, and we can output that. Otherwise, if exited was 0, then we know that the child was terminated by a signal, and we could then call wterm sig down here to get what that is. So here's what's interesting. If you call wexit status, which gets the actual exit status, on a child exit method integer that was in fact set because the process was terminated by a signal, then it will give garbage values. So and that can really confuse you. It might end up with something that is not what you expect. So if you make the mistake and check it when it was not prudent to do so, you'll get a garbage value, which then can, that'll be translated into garbage in, garbage out for the rest of your program. So now we're going to talk about something completely different. In this case, this is going to be, how do we actually start a process that is completely different than what we were running before? So if we had fork that's always making a copy of the current program, what if we want to start a process that's running completely different? That's a completely different one. So these, of course, is the classic thing from Monty Python's sketches, where they would be running a bunch of interesting, funny comedy bits, and then they would say, and now for something completely different, and change to a totally different era. Totally different thing, and it usually had John Cleese behind a desk to kick it off. Anyway, fun. I'm dating myself here. So for this, we use the exec family of functions. So exec is short for execute, and what it does is it replaces the currently running program with a new program that we will specify. So the exec functions do not return. They destroy the currently running program. So no line after a successful exec function call will run. You can pass in arguments to exec, and those are going to become the command line arguments that will be the argc, argv variants in C, and that would show up as the 1 and 2 positional parameters in a bash shell, for example. So we can pass in arguments to exec that will be used by the process once it actually runs. There are two different types of execution here, or two different ways of running the exec function. We're going to look at both major branches of exec, and there's two different ways to run each of those branches, so 4 different methods here. But here's a basic one. So this is exec with the L. And what this does is it's going to execute the program that's specified by the path to that to that program that you put into this first parameter. And then all of the rest of these, all the rest of the command line arguments are specified in a list from arg1 all the way through to argn, and that's what the L stands for. That's a list. So here's the path to the program, here's all the arguments to that thing. Exec v, on the other hand, this family, is about executing the program specified here at the path, and then all of the arguments are instead inside an array, and then it's argv array, and then you can get them out of the array yourself whenever you want. You don't have to read separate parameters, they're all in one parameter. And you can use either one, so both exist because there are different other functions and libraries in C that will return various bits of text in different ways. Sometimes they're returned as an array, in which case we might want to, we can stuff those directly into execv. Sometimes they're returned as a giant list, and so maybe you're string tokenizing those out and you want to put all those into execl. That certainly works too. Okay, so the current working directory in regards to this exec family. So execl and execv, they don't actually examine the path variable. They only look in the current working directory. There's a way around that coming up in the next slide, but they're not going to examine what the path variable has in there. So if you don't give it a fully qualified path name, then your programs are not going to be executed, even if they are in a directory that's in your path environment variable. And that will cause execl and execv to return with an error. Remember how we said they never return? Well, if they can't actually run the program that you've put in there, they will return and tell you, what are you trying to pull? This program doesn't exist. Try again. And to move around the directory structure such that you could use these two functions, then we would use get cwd for get current working directory, and change dir to set the current working directory to some new location. So this is how you would cd around and get your current working directory, so that we could put ourselves into a place where a program exists, so we could use execl and execv. There's an easier way though, and that is with the P variant of those two families. So this is execlp and execvp, and what the P stands for is path. So the versions that end in P search your path environment variable for the executable that you passed in. So in general, you'll want to use these versions. You're going to want to use the P versions because they're a lot more convenient. Instead of having to change directory around, you can just use the VP and the LP version, and know that as long as the program you're trying to start is in any directory that is included in your path environment variable, then it'll get started by exec. And if it doesn't, of course, these things just return and say, hey, this program doesn't exist, try again. Alright, so executing a new process. Exec replaces the program that it's called from. It does not create a new process. That's kind of interesting. So, a little example here. If we're going to use fork and exec, we can keep our original program going and spawn then a brand new process. This is how a shell works. Here might be, for example, a shell or a server process, and it's got process ID 4932. So that process just keeps running. And it happens to fork something off and create a bunch of other funny business. But from the perspective of this process, it no longer cares. It's still running, and it just goes off and does its own thing. It doesn't have to pay attention to the child processes, although it is good form to do so, and you can create zombies if you don't. More about that in the next lecture. But the parent doesn't care. Meanwhile, the child does care. The child has just been created, and because it has been spawned, it is a new process ID. This is 6923. This is running the same code that was running in the original process. So these are, if this was a server or a shell, then the cloned copy is the same server, the same shell. It's certainly started at the beginning of that fork call, so maybe you immediately if statement it off into a new branch of code, but it's running the same program. As soon as our process, our spawn process here calls exec, however, then it hollows out the contents of that process and loads in a new program. So we can load in, say, for example, the connect program. But our process ID hasn't changed. It's like it hollows the guts out and wears it like a skin. That got pretty dark. Sorry. Let's move on. So, oh, it's still dark. Sorry, I forgot. There's a knife that comes in and actually kills off your previous process, and the process ID hasn't changed, but it's brand new code. All right, so passing parameters into exec. So if we want to pass things, so here's an example for how to pass things into the list variant. So our first parameter is the path name of the new program. The remaining ones are command line arguments. Strangely enough, the first argument should be the same as the first parameter, so the command itself. The last argument is always null, which means there's no more coming in the list. That tells whatever program you're running to stop looking. And then you have to make sure here, this is kind of an esoteric point that'll make more sense as we look at the programming assignment for writing a shell here in this course, but you don't actually pass in any shell-specific operators into exec. So all the redirection stuff, whether it's the pipe operator or the file input-output redirect symbols or operators, or the ampersand, which is used for background commands, or the exclamation mark, which fires up the history command, these are all shell things. So if you want to do any funny redirection of files and file descriptors, you have to do all that before you call exec. Those changes will be preserved into the new process, but you can't put those into this exec function. Exec has no idea what to do with them because those are part of the shell, not part of the underlying kernel that's just trying to run this thing. So again, if you're trying to run ls-a, then you put the program itself here, and then the first argument is the same thing, and then the actual first argument. Kind of funny how this ends up looking. Here's a example for the LP version. This is a full example of it. So we'll start out with our spawn pit and our exit status set to junk values. We'll do the same fork rigmarole. Here's our exit status. Here's our exit branch if something horrible goes wrong. Here's what the child does. The child says that it's sleeping for a second, and that it is then converting itself into ls-a. And it does that by just calling exec lp. Here's ls for the second time, and then the -a. If it gets to this line, the only reason it would get to this line is if exec failed for some reason. Maybe ls couldn't be found or something like that. And if that occurs, then exit out with some error value and then break. And the break has to be here for compile. Obviously, the exit kills the whole process, but this break makes this thing such that you don't get funny warnings about how your statements from your cases are drifting into each other. Sometimes there might be a case to do that, but for the most part, it's a bad idea. All right, so in the default case, this is if the parent is going to hit this code. The parent says that it's sleeping for 2 seconds, and note that it's printing out its process ID, and here the child is printing out its actual process ID. The parent says that it's waiting for the child to terminate, and then it calls waitpid, which does block the parent. The parent will not continue any further until the child actually terminates. Once it finally does, then the parent says, oh, it wakes up and it says the child terminated, and it exits, and it talks about the actual process ID that was returned, and then exits itself with a normal value. Here's the output. So compile this thing, fork exec, and then run it. So exec. So the parent says, I am process 8201, I'm sleeping for 2 seconds. The child says, I am process 8204, I'm sleeping for a second. Then the child says, I'm converting myself into ls-a. So then it does. It's converted into ls-a, and here is its output. Here's all the stuff that was in this directory when this thing ran ls-a. Then, after that finishes, the child process finishes and terminates and exits. It's gone. And at that point, the parent wakes up, and the parent says, well, this line actually could have been anywhere, right? This is waiting for child to terminate. So because we told the parent to sleep for 2 seconds, and the child for only 1 second, the child was going to do its stuff first before the parent returns. But if we had not slept the parent, then this waiting for child to terminate could have been placed right up here after the parent call. In any event, when the child finally terminates, the parent knows about it, wakes up and says that its child, 8204, remember the parent's 8201, that its child terminated, and then the parent itself exits. So a complete example for showing how exec lp and the parent are able to fork off a new process which then execs into something different, and having the parent clean it up. Passing parameters into exec vp is very similar. So in this case, it's going to be a vector, which is where the v comes from, where all the arguments are organized before you call this thing. So the first one is the path name to the new program. The second one is an array of pointers to strings, each one which is the variable that you're using, the value of the variables that you want to pass in. The first string should be the same as the first parameter. So the first one of argv, again, is the same thing as the path. And then the last one inside our array also has to be null, which says there aren't any more in the array. Note that this is an unsized array, so the null tells C, the compiler, when it needs to stop. And similarly, don't try to pass any shell-specific characters into this thing because they're not involved. Here's an example. Here is an args array, so it's of size 3, and it contains ls, -a, and then null as the required final one. To run VP, the first argument that you pass into it has to be that ls. Then the second argument is everything. So you take the entire array and stuff it in, and that runs the whole thing. Kind of interesting. Here is an example for this again. So we're going to cat out our exec vptest.c. Then we have an execute function. So our execute function is going to receive a char double star, which is to say it is an array of pointers to strings, and we're going to call it argv within our function here. Then we're going to run execvp, and if it fails for some reason, then we'll go ahead and exit. And I've wrapped that into this if statement here with the less than 0, just to show you another way of running this. So execvp is going to take the first okay, so this here is the operator that is going to undo one level of the indirection caused by the pointer to pointer that the argv variable has. So this is our dereference operator that's going to de-address this thing. And essentially this is going to get the first argument out of the array. Whereas argv by itself, unadorned with any operators, means give me the entire array. So, right, print out if there's a horrible error. And then here is our actual main function as defined. And in main, we're going to define our array of ls and -a, and then there's the null. So here's our char star array, so an array of pointers to strings. Print out what's happening, replacing the process, and then here we have two strings that are being reported. The first one is the first argument, and then the second argument. So then we have the compile step, and here it is. Compile. We're compiling out to exec vptest, and then run it. And it tells us that it's replacing the process with ls -a, and those are what was stored inside those two variables. And then it terminates, or well, it replaces the current running code with the results of ls -a, and then terminates. So nothing too strange there. Let's talk about the exit function. The exit function is going to, there's lots of different ways to get into exit, and one of them is called @exit, and you can pass in a function into @exit, which basically says arrange for this thing to be called before exit happens. So whenever exit actually does get called later, then it will interrupt that procedure and run whatever function you register with the @exit function. Exit itself is going to do this whole list of things. First of all, it's going to call functions that were registered by @exit. It's going to flush any standard input-output output streams that it has buffered and send those out to wherever their final destination is. Then it's going to remove any files that were created by the temp file function, which is just another way to create temp files on the drive. And then it's going to call _exit. What _exit does is it actually terminates the process. It's going to close all the files, and then it'll clean everything up. So it actually terminates the process and starts removing memory and all that stuff. So you can check out the man page for wait, and it'll show you the complete list of what happens when exit actually occurs. Kind of instructive, kind of interesting. Return from main does the same thing as exit. So you can have the exact same bunch of little steps that's going to occur whenever you call return, because it does the same thing. Okay, environment variables. This will be our last subject for this admittedly long lecture on processes. And I should say that when I teach this in person, this we do this over a couple of 2 different lecture days, just because we always have so many questions. So definitely understand if this is long-winded. So environment variables, they are a set of text variables in the shell that are often used to pass information between the shell and the C program. They're handy if you have a special configuration for programs that we're calling a lot, so less or more are common pagers. Maybe we've got a specific way that we want to run those every time. We can register that with environment variables that are accessible by the processes we run. We can specify different configurations for lots of different things. Let's see here. We can view and edit the environment from bash by using the printf and export commands. These are bash ones, and the assignment operator. We'll do an example for that coming up. In the C environment, we can modify and look at environment variables with setenv and getenv, and I'm going to put a huge asterisk by this. The environment can be edited in C, yes, with the setenv command, with a big asterisk, so hold that thought. Print environment, if you just run this from the shell, it just barfs a huge amount of text onto your screen, and I've cut some of it out too just to make it not be as long. But it's got interesting things in here, like where the man pages are stored, where all the various manual pages are. It tells us the host name for where we're currently connected. It tells us things like the SSH client IP address we're using. Here's our full path variable. This is a colon delineated list. It shows us each directory it's going to search in whenever we tell it to run a command. And note that the final one is just the dot, meaning current working directory. So it will look in my current working directory whenever I run something if it couldn't find it in any of these other places first. This is an ordered search. Some people remove the dot off of their path variable because there's a tiny chance that there is a security hole involved with doing so. But it's really rare. It's going to be a lot easier if you add dot there. Anyway, here's the current working directory that I'm in, and a bunch of other stuff, so kind of interesting. Manipulating the environment. So in bash, we can manipulate our environment variables. They are basically just like normal variables. So they merely happen to be instantiated when your shell is created automatically. So if I want to create a new one of these, I create it as if I'm creating a standard bash variable. So myvar, for example, that's just a new variable I'm going to start using, so it gets created. I'll set it equal to the string, some text string 1, 2, 3, 4. The export command, what it does is it makes this variable available for child processes of the current process. So if I'm in a shell, a child process of a shell is any other command or process that I run that's not a built-in shell command. So we'll talk more about that in a bit. So then I can echo the value of this thing out, and then I can set new text into there. It's just a normal bash variable. In C, here's what the setenv call looks like, set environment variable. So you first name the variable you're editing, and you pass in a string, and then you can pass in various options here. The 1 means overwrite the value if it's already there, for example, and I think 0 is don't overwrite if it's there. We have to look that one up. Then we can get the variable back out by using the getenv function, which returns a string, which we can printf out. All right, but this is the giant asterisk. Manipulating the environment variable from inside a C program is just for you. So let's take a look at what this means. It's just for that process. So remember how we said everything gets its own unique execution environment? Well, here's that in force. Here's our program called bash and C environment.c. It has the standard header files, a main, a character array of 1,000 spaces, and I'm going to say that a particular variable has a value. And the value that I'm looking at here is going to be whatever the user types in. So you're going to, when you call this thing, so here's an example of it being called over here, you call it and then you pass in the name of some variable. So in this case, the first argument to this printf call is the name of the variable, and then get the environment variable means get the value of that variable and return it as a string, which is dumped into this part here. Indicate to the user that we're doubling it. So what we're doing there is we are string copying in the whatever the value of that thing, string copy it into array, and then we're going to string concatenate on the same thing again. So build up that string so we see it twice. And just as a little hint, you can see that over here. We just take our text dot and text dot text dot, get the same thing. Then we're going to print it out. So the new value will be this, and then indicate what the new value will be, the new value of the variable, what it will be. Then we'll set the environment variable. This is what actually records it into the environment variable at all. Without this, then we're just messing around with strings, right? So then we can tell the user what actually happened. We'll get env again from the same place that we just set enved. Okay, let's look at what actually happens though. So first of all, we set a variable called myvar, and we set it equal to some text. So 5 characters here, text dot. Export it, which makes it available for these child processes of the shell that we're in, and then echo it back out again, and we can see that sure enough it has a value, so nothing strange. Compile our program, no compile errors, everything's good. Run our program, so here's the name of it, and here is its argument, which is the name of the variable that we're going to examine. So the output is that the variable myvar has a value text dot, which is good because that's what we put in there. It tells us it's doubling it. It tells us that the new value of it is text dot because it did string concatenate on a clone of itself. And then it tells us that this particular variable has this value, text dot, and that came from the getEnv. So that's good. It actually did get written into the environment variable and then fetched back out again. Then our process terminates and completes. When we then echo back out myvar, note that it's just text dot, not text dot, even though we know that we wrote and then retrieved from that variable, the actual echo myvar doesn't have the doubled value. So all that work for nothing. What happens here is that the process execution environment belongs to only that process, and it gets its initial values from the parent shell, which is why myvar had data in the first place. But a process cannot edit the environment variables of its parent shell. That would be a major security hole if you could. So any modifications that you do to your environment is only useful for your current process, which makes editing them and storing new values into them not very useful. It's definitely not very useful at all. As I'm trying to think of a case for that, imagine you did have something like a shell where you're spawning multiple copies of processes. If the parent process is changing its values, those values stick in that parent process only. So the children won't see changes that the parent makes to environment variables either. So the use for this thing is fairly limited in terms of editing them in C. There's certainly value in retrieving them because we're getting interesting information about the environment, such as the path and the default shell and that kind of thing. But yeah, editing them, not much use in C. So exporting, just again to talk about what export does, this demonstrates how the variable is made available to child processes of whatever process was using it, whatever process is after the export. So here we're going to set up a new variable called myTestVar. We'll set it equal to some string, test text in this case. Echo it out. There's our value. No surprise. Here we run our same program as before with myTestVar, and it tells us that the testvar has value null, and tells us it's doubling it, and then segfaults. So what happens here is that this variable did not exist for this particular program. And the reason is because we didn't export it. So here we'll export myTestVar, which makes it available for child processes of the shell. Then when I run bash and C environment, again with the variable, I do get a complete run of this, and it shows us the value being doubled. But just like before, when this process terminates, we can echo this thing out, and it shows us, sure enough, it didn't stick. We only have the single version of it. What a bummer. Okay, so fork bombs, as a final closing thought here, a fork bomb is funny. It's where you manage to bring down a server because you've created a process that spawns copies of itself forever until some system administrator gets mad and kills all your processes. So while it's doing that, the whole thing gets slow and pokey, and in some cases I've even seen really, really bad fork bombs actually crash the server where it has to be restarted. So not very likely, but it's possible. So consider the following warning signs that you might be about to do something dangerous. So By dangerous, we're talking about you might consume all the system resources and you might get locked out such that you can't even terminate your processes because you've used up all the available processes allocated to you or allowed by you, so you can't spawn one more. So one dangerous thing, you've written a loop that inside that loop calls fork. That's dangerous. If you don't write that correctly, then and that gets out of control, that thing is going to spawn a billion copies. So another dangerous thing, you've written code in which your child process creates another child process. So this is a fork within a forked process. And this usually isn't what you want. Usually there's some master server that is in charge of spawning new copies, and each one of those copies goes and does its thing and terminates. Usually you don't have a thing where the child processes are creating copies of themselves. And another thing is that any place where you've got code that's written in which your child process is starting up some kind of a loop. So something to be aware of. Maybe there is a hidden fork that you didn't know about. Maybe inside that loop it's calling a function that contains a fork. So watch out for loops inside child processes. Again, child processes usually are things that are spawned, run to completion, and then stop. Often they'll have some sort of loop where they're waiting for input or something like that. But just be aware that that is one way or one place where fork bombs start. It's kind of the generalization of our first bullet point here. So last slide. Remember that you have to be really careful that you have termination methods built into your loops. Don't just start up a loop as a testing with a fork in there and think, I'll just run this and it's going to be great. I'll Control-C back out and re-edit my code. I just want to see whether this is working so far. That's how you kill the server. You got to make sure you've got the termination methods all built in. So a couple different methods for that, and you can think of your own fairly quickly, I'm sure. But consider having a variable set a flag called fork now, say for example, inside your loop. So it's some variable that gets set when it's time to fork. Then maybe you have some separate function call where it reads if the flag value was set, and if it was, then it calls the fork, and then it resets the flag back to don't fork the next time it comes through. So that way you have to explicitly be setting it each time. Now of course we can all imagine cases where you'd set that thing up such that it automatically goes off and creates a fork bomb, but you're just trying to create little extra steps you have to go through to make fork be safer. Another way to do this is that maybe you wrap fork around another function call where there is some sort of extra condition in there, some sort of counting variable that tracks the number of times fork has been called. So maybe you hit 25 or 50 forks, then you would call the abort function. Abort is different than exit. Abort just says die now. Don't do any cleanup. Don't be careful. Just immediately exit the program. So if you hit say 50 forks, then just die immediately. So that's kind of interesting. And now you know, and knowing is half the battle. All right, I hope this was instructive. And the next few lectures are going to talk about how we actually deal with zombies and signals. So that it should complete what we need to know for writing our own shell. All right, thanks again, and we will see you next time.